So we'd like to continue looking at some graph theory. Remember, we're looking at some graph theory where we have vertices, which are dots, and edges. Edges are the connections or the lines between the dots. We talked about a graph being traceable. Remember, traceable means you can basically draw every single edge exactly one time without picking up your pencil. So we want to give a new definition here. What does it mean for something to have an Euler circuit? What does it mean for a graph to have an Euler circuit? So definition, we're defining. So an Euler circuit, that's a path. Remember what a path is. A path is a sequence of edges that you don't ever repeat. So an Euler circuit is a path that begins and ends at the same vertex. That begins and ends at the same vertex. So it has to begin and end at the same place. So basically the idea is you're tracing the graph and you have to start and finish in the same place. So here's basically the criteria for there to be an Euler circuit in your graph. Criteria for an Euler circuit. And it says this. So you have to first of all have a connected graph. You can't have a disconnected graph. So a connected graph has an Euler circuit if and only if the following happens. If and only if. Every vertex has an even degree. In other words, there are 0 odd degree vertices. There are 0 odd degree vertices. There are 0 or no odd degree vertices. So all even vertices means 0 odd vertices, or 0 odd degree vertices. It's another way of saying it. Okay, so we want to do some problems here where we look for Euler circuits if possible. So here's some exercises. So here are your instructions. So part A, we're going to have multiple parts to each question. Determine if the graph has an Euler circuit. Determine if G has. Let me say the graph. Let me say the graph rather than G. Determine if the graph has an Euler circuit. That's the first part. Part B, after you do that, if not, add edges. So it does. And part C, list a sequence of vertices giving an Euler circuit. List a sequence of vertices that gives an Euler circuit. Okay, so basically we got 3 parts to our problem. So part B, you only have to do if it does not have an Euler circuit. You have to come up with some edges, so it does. All right, here's our first problem. Let's see. I got A, B, A, B, C, D, E, and F. And they're connected in the following way. A here to B, B here to C, C here to D, D and B are connected, D and A here are connected, D and E here are connected, C and E here are connected, E and F here are connected, and let's say D and F are connected here. Let me get this spider web looking thing. So part A, we want to figure out, okay, so it's obviously a connected graph. So part A, we want to first of all determine what's the degree of each vertex. We're not asked to do that, but we need to do that to figure it out. What's the degree of each vertex, so we can see, does it have any odd degree vertices? So degree of A, degree of B, degree of C, degree of D, degree of E, and degree of F. All right, what about A? It has what? Use blue here. Degree 2, right? A has degree 2, has 2 edges coming out. B has degree 1, 2, 3. C has degree 1, 2, 3. Yeah, that's 3 right there. D has degree 1, 2, 3, 4, 5. E has degree 1, 2, 3. And F has degree 2. So if you look at this carefully, you got some odd degree vertices, right? B, C, D, and E are all odd. So the answer here is no. No Euler circuit. Since there are odd degree vertices. Some odd degree vertices. That's part A. Part A. So if we had all even degree vertices, we would have an Euler circuit, but we don't. Okay, so part B, we want to construct some edges to make it so that there is Euler circuit somewhere. So here we go. This is going to be part B. So for part B here, I'm going to form some new edges. So which ones were odd, right? B and C were odd. So what we're going to have to do, we're going to have to take B and C, let's say, connect those. We can connect those. So you want to take a pair of your odds and connect them. And then we have another pair, right? D and E right here, right? D and E, they're both odd, so we can connect those. So we can put an edge between D and E. Let's just put an edge between D and E. So what I'm doing here, I'm putting edges between every pair, well, not every pair, but certain pairs of odd degree vertices. So I took one pair of odd degree vertices, B and C, and I put an edge between those. And then I took a second pair of odd degree vertices, D and E, I put an edge between those. So that's going to now make the degree even. So if you actually look at B right now, focus on B, there are actually 4 edges coming out of B now. As for C, there are 1, 2, 3, 4 edges coming out of C now, that we added that green edge. If you look at D, there are what? 1, 2, 3, 4, 5, 6 edges coming out of D. And E, there are 1, 2, 3, 4 edges coming out of E. So you don't have to add those exact edges, but those are the ones I decided to add. So what did we do? We added BC as an edge and DE as an edge. All right, now, the final thing we have to do, part C, you got to come up with a sequence of vertices. Maybe I put this in the wrong place. Let me put this up higher. Sequence of vertices that gives you an Euler circuit. I'm going to put this up higher. This would be part C. Part C. Now, you can start anywhere on your graph when you're trying to trace this. So the idea is you want to trace this. To find an Euler circuit, you want to trace this. You want to start at a point and you want to end at the same point. So where can I start? I can start anywhere. I'll just start at F. Let's say I start here at F. Okay, I'm going to write F. It's my first vertex. Now you got two options, right? You can go E or you can go D. I'm going to go E. So I went from F to E. Then from E I can go here to C. Okay, from C I can go to B. I'm going to use this new edge I created, the green one, C to B. B, I'm going to go to A. A, I only have one option. I have to go down to D. Now, from D, I have several options, but I don't want to go to F, because if I go to F, I go back to where I started and I haven't traced everything. So I have to go somewhere else. Let's go from D to B. And then from B, we only have one option, right? We can go to C. Then from C, we only have one option. We go back to D, comma. From D, I have a few options. I'm going to go over here to E. And then from E, I just have, let's see, one option. I have to go around here back to this green loop to D. And then from D, I have one final option back to F where I started. There's my sequence of vertices. Traces that new graph that I created from those two green extra edges. I had to create those two green extra edges to make it traceable. All right, you got part A. No, there was not an Euler circuit. Part B, we added two green edges, BC and DF, to make it traceable, starting and beginning in the same place. And then we just listed a sequence of vertices that would take us through every edge, start and end at the same place, giving us an Euler circuit. All right, let's do another one. Another graph. Let me see. A, B, C. C, E, F, G. All right, I'm going to connect A to B, B to C, C to G. All right, A to E. E to F, F to G. A to F, C to F. What else? B to D, D to F, A to D, and D to C. There's my graph, all right? So first of all, we got to figure out, is there an Euler circuit? Can you trace it and start and end in the same place? So part A, I'll do it in blue. So we're going to figure that out. We're going to look at the degree of each vertex, degree of A, degree of B, degree of C, degree of D, degree of E, degree of F, and degree of G. All right, A has what? 1, 2, 3, 4 edges. B has what? 1, 2, 3 edges. C has what? 1, 2, 3, 4 edges. D has what? 1, 2, 3, 4 edges. E has what? 1, 2 edges. F has what? 1, 2, 3, 4, 5 edges. And G has what? 1, 2 edges. So we can already see that this dude is not going to be having an Euler circuit because it has some odd degree vertices, right? B and F are odd degree. So no, not it, no Euler circuit. Since there are odd degree vertices. Okay, so right now as it stands, you're not able to find an Euler circuit because you got odd degree vertices. But what you can do, you can take those two odd degree vertices, B and F, and connect those. So let's see. How can we connect B and F? Well, we can just take a big old loop around here, big green loop. It goes around from B to F. So you take your odd degree vertices and make a pair. Make a connection between a pair. So if we had a second pair of odd degree vertices, we could connect them with an edge. All right, so part B was to actually make this pair, right? Join them together. So we just we added BF as an edge, right? BF. And just tell them what I did there. Part C. Now we actually have to find an Euler circuit. Euler circuit. So we said there was not an Euler circuit initially, but because we now join B with F, we can find an Euler circuit. So where do we want to start? We can start anywhere on here. Let's start at G. I'm going to start at G. I'm going to go around here to C. From C, I can go in a lot of ways. I can go to B here. From B, I'm going to go up here on this new green loop that I just added. I'm going to follow this over to F. All right, we're at F. Now, if I went to G, I could close the circuit. I'd be back at the beginning, but then I'd be missing a lot of my, I would be missing a lot of my graph edges. So I'm going to go from F to E here. And from E, I'm going to jump around to A. And from A, I'm going to slide over to B. Now basically, I only have one direction. From B, I can go to D. From D, I can go up to C. From C, I can go back to F. Now, I can close the circuit and go back to G where I started, but I don't want to do that because I'll be missing part of the graph. So what can I do? I can go, let's see, I'm at F. I can go up to A. And from A, I can go down to D. That's the only way I can go right now. From D, I'm forced to go down to back to F. And now I can close the circuit and the G. And that traces everything. I started and ended at the same place. So there we go. Pretty cool, huh? Pretty cool. All right, so here's our law. I'll do one more example. What's this one look like? Let me see a picture. This is like a pentagon and a pentagram inside of a pentagon. So I got what? 1, 2, 3, 4, 5. A, B, C, D, E. So we got a 5-pointed star inside of a pentagon. All right, so first of all, we got to figure out, is there an Euler circuit? Euler circuit means, can you trace this graph? That means you draw every edge without picking up your pencil and start and finish in the same place. All right, so we're going to look at the degree of each vertex. Degree of A, degree of B. So if they're all even, the answer is yes. If we get some odds, the answer is no. Degree C, degree D, and degree E. All right, what's A? A has what? 1, 2, 3, 4 edges. What about B? 1, 2, 3, 4 edges. Degree of C, 1, 2, 3, 4 edges. Degree of D, 1, 2, 3, 4 edges. And E is what? 1, 2, 3, 4 edges. Hey, everyone has 4 edges. So we have all even edges in this connected graph. So that means yes. So this is a yes situation, since yes, there is an Euler circuit. Since all vertices have even degree. Okay, so for part B, we don't have to add any edges. So I'm going to write NA, right? NA does not apply. We do not need to add any edges to make this dude have an Euler circuit in it. So for B, when you don't have to add any edges, just write NA. All right, so we're ready now. The final step. We just got to find an Euler circuit here. This is part C. Find an Euler circuit. So I'm going to start here at A, go to B, go to C, go to D, go to E. Now I don't want to close my circuit here, because if I go back to, well, I guess I could go to A, right? I could go to A because there are other places I can go now. I can go back to A. Yeah, let's just go back to A. From A, we can go to some other place. We can go to what? D, for example. From D, where can we go? We just have one option. Over to B. From B, where can we go? We only have one option, right? E. From E, where can we go? One option. C. So I'm at C, where can I go? I'm forced to go back simply to A, and I'm ending where I started. And I traced everything. Yeah, pretty cool. All right, so I mean, it's really more of what we were doing earlier with tracing, except we want to make sure we end and beginning with the same place.